Good afternoon, everyone. First of all, thank you for attending this talk. My name is Sujith. I'm a machine learning researcher within Microsoft, and I'm mostly focused on resource-optimized machine learning, both computer vision and natural language processing. And it turns out Forrest, who's been a friend of mine for a decade, is an expert on both topics. Natural language processing is a very interesting topic, both from product perspective, from Bing to Cortana running things on device, and there's industry-wide interest in this topic. Now, Forrest is here to talk about his journey from SqueezeNet to SqueezeBERT and what we can learn specifically from utilizing aspects of convolutional models, such as group convolutions, to really make language processing much more efficient. Here's a brief bio. Forrest is kind of part of the extended Microsoft family as well. Has been an intern at Microsoft before. Has given a few talks within our own group as well as the broader Microsoft community. So let me quickly read his bio. Forrest Iandola completed his PhD in EECS at UC Berkeley, where his research focused on deep neural networks. He's best known for deep learning infrastructure such as FireCafe, deep models such as SqueezeNet and SqueezeDET. His advances in deep learning led to the founding of DeepScale, which was acquired by Tesla in 2019. He's now an independent researcher focused on squeezing deep neural networks. He's well known for the Squeeze family of models, so SqueezeNet, now SqueezeBERT. Hopefully we've all read the paper. If not, let's take a quick look and let's hope to learn a lot more about squeezing deep neural networks, both vision as well as natural language processing models from Forrest. So Forrest, it's all yours.
Thanks for the very thoughtful introduction, Sujith. So I'd also, in addition to thanking Sujith for bringing me in to present this to you, I'd like to thank Albert Shaw, Ravi Krishna, and Kurt Koitzer, who are great friends of mine, some of whom I've been working with for many years, for their contributions to this work. And so what I'd like to do in this talk is to begin by reviewing, in the last 5 years, what have been the key discoveries and breakthroughs that have enabled computer vision to become much more efficient. And then, given that natural language processing right now is in a renaissance era where things are improving very rapidly at the cost of computation, however, I'd like to look at, if we take the findings from computer vision research and how we make computer vision efficient, how might we bring that to bear on making natural language processing also more efficient? And as a first step in that direction, I'll present some of our recent work, SqueezeBERT, and I'll also propose some future directions for this work. So starting with computer vision, so as many of you will probably point out, there are probably hundreds of different computer vision tasks, and many of which are quite useful and important. But if you look at the very core of the computer vision research community, 3 of the tasks that people spend an inordinate amount of time on are image classification. So you look at an image like this on the left, and you want to say something about the entire image. So you might say sedan, or another reasonable answer would be roadway. In the middle, we have object detection, where we want to label the individual objects and decide what kind of objects they are based on categories, and also draw a rectangle or cuboid around them. And then on the right, we have semantic segmentation, which is a very detail-oriented task where we want to classify every pixel based on what kind of object it's a member of. And so here we just have a basic example of sedan and road, but we can get very advanced with this as well. So in the next few slides, I'm going to talk about some of the advances in image classification and semantic segmentation in the last half decade or so, and look at the improvements both to accuracy as well as to efficiency. So image classification, if we look at where we were in 2015 or 2016 on the very widely studied ImageNet benchmark, ResNet, on here I've shown ResNet 50 and ResNet 101. was in the 75, 76% top one accuracy range. All the numbers I'll be talking about here today are single model, single evaluation. So no funny business with big ensembles or running the image through the network many times or anything like that. Just basic networks. So and then SqueezeNet was one of the first networks in the image classification arena where we really pushed on efficiency. And the flop reduction, versus ResNet is large, although the accuracy is lower. We also improved flops over AlexNet, which is more kind of a similar accuracy as SqueezeNet. But the other big win, which I'm not showing in this slide, was that SqueezeNet had far fewer parameters than most other networks. So that was kind of the lay of the land 5 years ago. And lots has happened since then, leading up to today. This recent family of models called EfficientNet, and even more recently, there's this paper from Facebook called FixEfficientNet, which further improves the quality of results from EfficientNet just a little bit. And the way we're showing this is that the FixEfficientNet is a family of many different models with a common architectural design, but that can be scaled larger or smaller. So one interesting thing is the accuracy with FixEfficientNet, especially out on the right here, has improved over ResNet in the last 5 years. The improvements I think are slowing down a bit year over year versus what they were a few years ago, but the improvements are still happening. But the other thing, as someone interested in computational efficiency and making things run fast, the other thing that I find exciting about this is if you look at ResNet 101, so this gray dot off to the right here, the ResNet 101 and even ResNet 152 have been surpassed in accuracy by the very lowest accuracy version of FixEfficientNet. And the jump from ResNet 101 to the lowest accuracy FixEfficientNet is actually a 40 times savings in the number of computations, number of flops. And I'll talk later about whether flops is an ideal metric, but it's certainly a metric that people use. And so that's been a big improvement. We've also seen similar kinds of improvements on semantic segmentation. So here we're looking at a data set called Cityscapes. That's quite popular in the semantic segmentation community. And going through time here on the right, we have fully convolutional networks, FCN, which came out in 2015, actually by some of my friends at UC Berkeley when I was a graduate student, did that work. DeepLab v3 Plus is another, I think, kind of watershed moment for advancing semantic segmentation accuracy. That was a big jump. Interestingly, the computation, on the horizontal axis was improved with DeepLab v3 Plus, and the accuracy also went up. And then finally, in terms of very, very efficient, low-cost models, all the way on the left here, we have a family of networks called SqueezeNet that I helped to develop with some of my colleagues. And the worst accuracy version of SqueezeNet is still more accurate than the state-of-the-art in 2015, and it has 160 times, not 160%, 160 times fewer computations than the 2015 state-of-the-art network. So we've seen basically both. If you constrain, if you freeze the accuracy that you're aiming for, if 2015 or 16 accuracy was sufficient for your application, we can now do that, in orders of magnitude less compute. And then also, if you're willing to use amount of compute that would have been reasonable in 2015 and do that again today, you can get far more accuracy than you could a few years ago. So there's been lots of progress on this. For ImageNet stuff I just talked about, that's all on a fixed data set, so no data set changes at all. This progress in semantic segmentation here, the only thing that really changed in terms of data sets from 2015 to present is people now often pre-train on the COCO data set in addition to ImageNet, and that often buys you 1 to 2 points on this class IOU metric. But by and large, these improvements are not from varying the data set so much as they're from developing superior neural networks and training them really well. So if we look at, particularly from a neural architecture perspective, what has enabled these improvements in recent years to both efficiency and accuracy, there are many things, but I've narrowed it down to 3 extremely important ingredients. So the first one is what are called grouped convolutions. And for those who haven't really thought about this before, let me give you kind of an intuitive explanation of what this is. So what I'm showing here on the left is a weight matrix. So I'm just doing a very simple neural network layer where the filter size is 1 or 1 by 1, and then there are 8 input channels and 8 output channels. And normally this matrix would be dense. So with a traditional convolution or with groups equal 1, this would be a dense matrix. And let me just color some of these columns so that we can watch the progression as we adjust the approach here. So that's groups equals 1. If we set groups equal to 4, so group convolutions with groups equals 4, this is the new pattern. So all these empty cells are now just empty, and we have this nice horizontally block sparse banded matrix. And this is something that, given that the neat sparsity pattern, it's not random sparsity, it's you set the sparsity pattern before you even start training your neural network for the first time typically. You can also take advantage of this when you store your weights. So you can take B here and organize it in the way we have in C and not waste any space. So this is the basic intuition behind group convolutions. This is something that was introduced, at least to my knowledge, the first time I saw this idea was in the original AlexNet paper. And people forgot about it for a few years, for the most part, but it came back in papers like MobileNet. And since then, this has been a common fixture in the efficient neural net community for computer vision. So that's group convolutions. The second innovation I want to talk about that's gone from being a rarity to commonplace in the design of neural networks with efficiency in mind is dilated convolutions. So this animation actually, I think, explains it better than I could explain it verbally. So on the left, we have a normal 3x3 convolution. This is just showing with one channel. In reality, this would be this pattern, but over many channels. Normal 3x3 convolution, you see the filter is dense. And on the right, the dilated 3x3, it's basically a 5x5 convolution, but with this pattern of weights removed. So it has the number of computations and number of weights that you'd see in a 3x3, but it has the receptive field of a 5x5. And in many areas of computer vision, maybe most principally in semantic segmentation, dilated convolutions have helped significantly to improve both the speed and accuracy of these networks. And then the third innovation I want to talk about is neural architecture search. So this slide, I admit, is a bit busy, but let me kind of step through it little by little. So if we think about neural architecture search, one of the fundamental things we want to do is, we want to design a network. We have several ideas for what each layer of the network could be, but we want some sort of automated way for choosing what those layers will be. So we first define a search space. So in the top wide box on this slide, we have these network layers that I'm just calling module 1, 2, and 3. You might think that module 1 is a particular type of convolution dimension. Module 2 is another one. Module 3 is a third one. And I think from about 2015 or 16 through 2019, the way that a lot of people addressed this problem of how do we get algorithms to help us design networks where we create a search space and then the algorithm tells us what's a really good network in that search space was reinforcement learning based architecture search. And Kwok Lee and others have been really big on this in the past. And the basic approach is you have a reinforcement learning controller that also has weights. And you have the controller propose a family of neural networks. Those get trained. The controller looks at the results on some sort of validation set. And depending on the results, the controller updates its own weights and then uses that to propose a next family of networks and iterates several times. And so this can be effective. I believe MobileNet v3 was actually developed using this approach, but it's also very costly. So if you're starting with some sort of system where to train a good network takes 1 GPU day, you can easily train 1,000 networks using RL to find one really good one. And that can add up to thousands of GPU days because you're doing all these independent networks trainings. And so at Google, that may be feasible, but for a lot of companies who have limited budgets, this is very expensive. So on the right, we have super network-based NAS. Recent work on this includes FBNet, DARTS, and our own work, SqueezeNet, which I'll talk more about later. And in super network-based NAS, Some people call this differentiable architecture search. I like to call it super network-based NAS. Instead of having lots and lots of independent networks, we create one super network. So at each stage of the network, we insert all the different modules that we'd like to be potentially used in the architecture search. And then there are different methods of selecting which module to use, but I would say a popular one is called the Gumbel softmax approach. And in that, basically at the beginning of training, all the modules are trained. It's just one big network. But gradually, through the use of parameters that are used to select modules, to select the best modules based on the backpropagation gradients, you gradually, by the end of training, end up with one subnetwork in here that's deemed by the architecture parameters to be ideal. And you can do this super network-based NAS if you want to, just purely optimizing to get the best accuracy. Or what more and more people are doing these days is also optimizing for efficiency. So in addition to just backpropagating the loss based on your classification error, you can also take that loss and for each module in your network that you're searching over, add a cost of that module to the loss. So that cost could be based on number of floating point operations. It could be based on latency. It can be based on memory consumption or whatever you deem to be important. And so in that manner, super network-based NAS can be used not only to create very accurate networks, but to trade off accuracy for efficiency in an automated way. And given that you're basically building one network and training all this together, relative to some baseline single network, this often adds up to something on the order of 2 times to 10 times the cost of just training an individual network. So these are 3 innovations that I think have been very, very influential in terms of getting more efficient networks. And so far, when we talk about efficient networks, we've talked about computations or flops to represent, how much a network costs. But oh, I see a question. So it says, so Chini Krishna asks, for NAS, most used metrics are flops and latency. Are there any other metrics you found to be successful? Yeah, I have seen 1 or 2 papers recently on optimizing for memory consumption. And the most interesting one of these was where, I forgot the name of the paper, but it was where you look at an embedded device like a microcontroller, and they have very hard limits on how much working memory you can use. And so they were using NAS to basically constrain the maximum working set required in a network, so that you don't go beyond the memory capabilities of the hardware you're running on. But yeah, lots of interesting things with memory I think are also possible. And I also am interested personally in, given that, as I'll show in a minute, different processors exhibit different latency for a certain network design. You may want to have a network that's portable across processors. You could chain together. You could say, well, I care a lot about this particular GPU running fast there, but I also care a lot about this particular cell phone processor. So I'm going to actually add the cost of the GPU latency to the cell phone latency to the original loss, and sort of jointly optimize for multiple systems. But there are probably many other things you could do. I think you could probably think of other things. So that question plays just into what I want to talk about next, which is optimizing for flops is interesting, and on certain platforms like, say, mobile CPUs like ARM CPUs, flops do correlate fairly well with latency, but that's less true for some other devices. And so to give you an example of this is for these 2 diagrams are from a paper that I really like and actually recommend reading called mBench, which came out last year, citations at the bottom. And these authors set up the several published neural networks ranging from MobileNet to VGG to others. And then they do inference with the batch size 1, which is a good setting for real-time inference on a variety of different hardware devices. And a couple of the ones that they do are on the left, the Movidius compute stick, on the right, the NVIDIA 2080 Ti GPU. And the most interesting thing about this to me is, so MobileNet is a couple orders of magnitude fewer flops than VGG. And on Movidia's compute stick, you do indeed get a pretty good speed up, when you go from VGG to MobileNet. And it's not as much as the flop savings would indicate, but it's 5 times. A 5 times speed up is pretty good. But interestingly, on this NVIDIA GPU, VGG16 is actually faster than MobileNet V2, despite the fact VGG16 costs a lot more in terms of flops. So this motivates a couple things, actually. One is that we really think carefully about our implementations of neural networks. I think there may be ways to implement MobileNet more efficiently on NVIDIA, but I haven't seen a lot of successful work on that yet. But the other thing is I don't think we're ever going to be able to get away from the problem that different neural networks run at different speeds on different hardware, and those speeds don't necessarily correlate all that well with flops. And so, sort of putting our money where our mouth is, we've been working on this problem in terms of optimizing latency using architecture search. So this is sort of some highlights from a paper called SqueezeNet that we did last year. And in this case, we're optimizing for a small mobile GPU. And we're showing 3 lines on this graph. So the green line at the bottom is what happens if we create a search space for semantic segmentation network on cityscapes, and we create a search space that has grouped convolutions and dilated convolutions in it, the 2 innovations we talked about before, and then we just purely search for the fewest flops that we can get per accuracy. And as you can see, the curve is okay, but it's actually worse than MobileNet V3 when you do latency versus accuracy, or in this case IOU comparison. But when we, instead of searching over flops, when we search for accuracy with the cost in our super network-based search being latency on this orange line, we actually get out ahead of MobileNet V3. And so optimizing for latency on the target device is really important. And in the natural language processing work that I'll be showing in a bit, we're focused much more on latency than on reducing flops. So to summarize what we've covered so far, so in computer vision, in the last 5 years or so, we've seen major reductions, sometimes even 2 orders of magnitude, in the compute cost in terms of flops to achieve a result without changing the accuracy. Actual speedups, in my experience, on the right hardware tend to be maybe more like 10x rather than 100 or 160x. But still, we've seen a lot of improvements there. And then also, if you freeze the compute cost but are optimizing to increase the accuracy, we've seen double-digit improvements in the accuracy on ImageNet, and double-digit improvements on the intersection over union metric on segmentation, and the same pattern holds for many other subfields within computer vision research. And just to review some of the key ingredients, there's certainly more, but some of the key ingredients that I think have made a really big difference in enabling these results are grouped convolutions, dilated convolutions, and the development and many improvements to neural architecture search algorithms. So now I want to move on part 2, which is efficient neural networks for natural language processing. And we'll start off just explaining, at least from my perspective, why efficiency in deep neural networks for NLP matters. I'll give some background on some of the recent advances in self-attention networks for NLP. Some people call these transformer networks. I prefer the term self-attention networks. And then we'll go into what we did in SqueezeBERT to improve efficiency and compare it to some of the other results. So first of all, why develop mobile NLP? And I guess I'm talking here about mobile NLP, but I think some of the same principles should apply to very efficient cloud NLP. So why develop efficient NLP? Well, humans write hundreds of billions of messages every day, just on Gmail and these few social clients, probably more across other platforms as well. And if you look at where we're actually writing and also reading these messages, so much of it's happening on mobile. So more than half of emails are written on a cell phone, are read on a cell phone. And on Facebook, which is where a big chunk of these 300 billion messages are moving around through chat, through statuses, close to half of Facebook users only ever use Facebook from their phone. And so I think natural language processing, especially with recent improvements to accuracy, has the potential to really help us be more productive in terms of more efficiently reading, understanding, prioritizing, and even writing messages. And in a few slides, I'll get to some concrete examples of different things you can do with NLP that facilitate this. And if you look very broadly at NLP, from my perspective, there's kind of two big areas. There's certainly others, but two areas that are just really, really widely studied right now, and that have been disrupted by the invention of self-attention neural networks such as BERT or GPT. So the first of the two areas I want to touch on is called natural language generation, or NLG. So these are tasks like machine translation, like English to Chinese, sentence completion, where I start writing something and it gets auto-completed, as well as generative question answering, where I ask a question and through the same mechanism that the autocomplete works, the model proposes an answer. And some of the recent networks that have become famous for doing this are the original transformer network from Google, published in a paper called Attention is All You Need around 3 years ago. There's more recent ones such as Transformer XL, the GPT family, and the Microsoft Turing NLG network. So that's language generation. Then you also have language understanding. So some language understanding tasks. So one is something called extractive question answering, which is similar to generative question answering from a user perspective. I mean, you ask the computer a question, it tells you an answer. But while generative question answering is just kind of doing an autocomplete, based on whatever it's learned in training, generative question answering, you give the network a question, but you also give it a fact set. You could give it a pile of textbooks. You could give it recent current event news or whatever, and the network you'll ask it a question, the network will point to what are the most relevant passages from these source materials. So I think extractive question answering, while it's maybe slightly less sexy than like GPT-2 or GPT-3, where it just automatically generates answers from training data, the nice thing about extractive question answering is you can continue to feed the network current events, such as recent news articles or recent publications on COVID-19 as it advances day by day, and extractive question answering can help you with that without retraining the whole model. So that's pretty cool. And then the kind of bread and butter task in NLU is text classification. So basically, you give it a sentence or maybe even a book, and it'll tell you based on some set of categories what it sees, similar to image classification in computer vision. And some of the popular models here are the original GPT, focused quite a bit on NLU, BERT, Albert. And then also there are some things like Roberta and Electra. Some people will say Roberta or Electra are model architectures, but in reality, Roberta takes the BERT architecture just off the shelf, and the Electra does very minor modifications to BERT just in the first layer. And the real innovations in BERT and Electra are in the training. So in Roberta, they add much larger amounts of training data, and they also train longer, and they do a few other things. In Electra, they're doing a discriminator generator approach somewhat similar or inspired by a GAN, or generative adversarial network, and that helps accuracy quite a bit. So anyway, these are areas where everything on this page, the state of the art in these areas, on many of the benchmarks at least, is now based on self-attention networks, such as the ones that I'm listing here. So one of the canonical self-attention networks is BERT, and there are a few different flavors of it, really large ones, smaller ones. One is called BERT-base. And one thing I want to start out by looking at, under the heading of efficiency, is, well, how fast does BERT-base run on a smartphone? If we want, as we type things, as we receive emails, to just be immediately, to get the results of BERT inference at our fingertips, how fast does that really happen? And right now, I took BERT-base in PyTorch, exported it to a self-contained PyTorch representation called TorchScript, put that on the Google Pixel 3 smartphone. It took 1.7 seconds to do a length 128 sequence. So that's, you take a sentence, you tokenize it, so you convert the words into integer values based on the vocabulary. And if you have 128 tokens, it takes 1.7 seconds. You might ask, is PyTorch the best, or are others faster, or what? So I looked up some results doing the same experiment on the same phone with TensorFlow, and what I saw was that BERT-base takes about 1.5 seconds there, so very similar. So this seems to be the reality of what we're faced with when running neural networks for NLP on a smartphone. It's pretty slow. So now let me talk about how BERT module works, and then I'll get to where the time is going, and then we'll work on optimizing the module design. So this, there are many diagrams out there for showing the BERT modules. What I decided to show here is a breakdown of all the layers and how they feed into each other, as well as what are the sizes of input and output. So this BERT module has these three fully connected layers called Q, K, and V. In the original Attention is All You Need paper, Q, K, and V stood for query, key, and value, and there were some things with passing results from early layers into later layers as one of the Q, K, or Vs. But nowadays, I don't know if query, key, and value really is the best analogy anymore. I just look at these as three fully connected layers that all just process the input data. And then where the attention actually happens in this module is in these two matrix multiplications. So you take the Q and K layer outputs, you do a bit of transposing and reshaping, and then you multiply them together. And the reason this is attention is, well, most neural networks that I've seen, the thing that the fully connected layer or convolution layer does is it multiplies weights by data, right? Attention multiplies data by data. So it takes the output of two layers and actually multiplies those together. And doing that has many interesting properties, such as based on the input data, you can re-rank which are the most important channels to be looking at, for instance. There are also ways that you can think about attention as connecting different elements of a sequence. So this is the self-attention piece, and it uses this QK transpose divided by constant, softmax that, and multiply it by the V tensor. So that's attention, and then the full BERT module also has these three fully connected layers at the end, often called feed-forward network layers, or FFNs. So we have four of these at the end, and yeah, that's a full BERT module. A BERT-based network first has an embedding layer, which takes the tokenized sentence and outputs a vector for each potential token. And then the whole rest of the network until the final classification basically is just 12 of these modules that you see on the screen here stacked up one after another. So if we look at where the time is going in this, particularly on our Pixel smartphone that we're using, what I found was that 88% of the overall latency of this network is from the fully connected layers. So the attention, the matmuls that we talked about, those are actually pretty cheap, both in terms of flops and in terms of latency, but these fully connected layers are quite expensive. And so, given, my experience working in computer vision for some years, when I see a really expensive layer, one of the things I think about is, well, could I make it into group convolution? And I'll get to that in a minute. But basically, the first thing is we have to figure out, well, is there a way to rephrase these fully connected, or sometimes people call them position-wise fully connected layers, as convolutions, so that we can then have the full range of convolutional capabilities at our disposal. By the way, I see you have a backlog of questions. I will catch up with those in just a minute. The two equations on this slide, one for fully connected, one for convolution, they're very, very similar. And in fact, the only difference is this K factor here on the bottom right, which is to account for the kernel size and having to reach out of your immediate point on the tensor to encapsulate your whole kernel size. But the thing is, if your kernel size is 1, then these two equations actually are equivalent, because that K just becomes 1. or becomes 0. So we go into this more in the SqueezeBERT paper, but this basically is our proof that what we've been doing all this time in BERT actually is a form of convolution. And so in the new model that we're proposing that we call SqueezeBERT, it's very, very similar to BERT. We've changed very little about the model relative to BERT. We've got the same embedding layer. We've got the same final classifier. We've got the same training mechanism. But what we've changed is for out of the 6 fully connected layers in the BERT module, for 5 of them, for Q, K, and V, and then for 2 out of the 3 FFNs, we have set them to have groups equals 4 instead of groups equals 1. So this, as we will see in a moment, can save us quite a bit of computation. But before I go into the evaluation, let me take a look at the questions and catch up on that. Right. So one question a while ago was, should we measure flops or energy? Flop seems like an incomplete metric. Yeah, energy is a really good one too. It's actually hard to measure the energy on a smartphone because it has a battery, and you need to kind of take it apart to get to the individual leads that you want to measure. But that's something worth doing for sure. And then someone said, I don't see many NAS papers nowadays. Has that reached some plateau? I don't think so. I think people are branching into new applications. But I think, and there is this paper called FBNet V2, where they go even further than I've seen before in terms of weight sharing across and amortizing computation across different layers in your search. So yeah, there are more questions. I will address the rest at the end, but I just didn't want to keep you waiting. So okay, that's the SqueezeBERT module. Now let's talk about how well it really works. So we're going to evaluate SqueezeBERT relative to BERT and another network or two on something called GLUE, which stands for General Language Understanding Evaluation. This is a natural language understanding benchmark set. It's primarily focused on text classification tasks. And just to give you a brief summary of what are the tasks in here, you can certainly check out the GLUE paper and find more, but just a bit of information. So there's one task on sentiment analysis, which I think could be really interesting for flagging, what are the unhappy customer complaints or reviews or help desk messages or things like that, and trying to bring them to someone's attention to address. There's several similar but not quite identical tasks on taking a pair of sentences as input and classifying whether they're similar, have similar meaning. And there's 6 tasks like this in the GLUE evaluation. And these, an NLP expert will tell you that each of these tasks is slightly different. For instance, some of them are just saying, given 2 sentences, do they mean the same thing? Others are saying, given sentence 1, does it imply that sentence 2 is true? So there's subtle differences, which is why we have so many benchmarks on this. But it's basically sentence pair matching is the basic idea. And then there's one that checks to see, given question answer pair, does the answer, at least from a grammatical perspective, answer the question? So that would be pretty useful, I think, if you're doing something like, a stack exchange or an issue tracker or a help desk, where you've got this backlog of email threads or forum discussions, and you can go, which ones do I need to not worry about anymore, because they seem to have been addressed. And finally, there's one task called COLA, which you give it a sentence or a sequence, and it tells you whether it thinks, the model's supposed to tell you whether the sequence is grammatically correct. So that could be useful, going beyond the current capabilities in grammar check and spell check as you write text. So anyway, that's what's in GLUE. And now let me show some results. So first, let me caveat this by saying in the paper, we read every conceivable paper we could find on efficient neural networks for GLUE, and cited them and put a big results table in there with tiny BERT and distill BERT and all these things. But for this, I just wanted to keep it simple and show BERT-base, mobile BERT, which I think is the best of the related work that I'm aware of for this problem around this level of accuracy, and then finally SqueezeBERT. So what's interesting here is, and these are all the latency are measured by me, but the mobile BERT latency I measured actually is slightly faster than mobile BERT latency that the authors reported, so I took the faster number. So anyway, what we find is mobile BERT has a bit fewer flops than SqueezeBERT, but then SqueezeBERT actually is more efficient in terms of latency, in terms of real speed up. So this is interesting. It tells you yet again that not all flops are created equal, depending on the device and depending on the computation. You know, the cost per flop may be higher or lower in terms of latency. But basically, you know, these are all around the same glue score. You know, we're doing some work to potentially further improve the results of SqueezeBERT. But I would say that glue results in the last couple of years, or maybe 18 months since BERT, have continued to improve. They're now in the high 80s, low 90s. So plus or minus a tenth of a percentage point here is not that interesting. And what would be much more interesting would be to take not just SqueezeBERT, but grouped convolutions and other bright ideas from computer vision and other fields and begin to apply them more broadly to NLP. So to summarize all this, I think computer vision research has made a lot of progress recently, lots of gains in efficiency and accuracy. Self-attention networks, otherwise known as transformer networks, have been a big breakthrough for NLP accuracy, but at the cost of more computation required. And so SqueezeBERT showed that group convolutions, which are widely used in efficient computer vision, can accelerate the recent network designs for NLP. And one thing I'm very interested to do in the future is to unify more of this. So I already have a initial implementation of neural architecture search for NLP, and I'm experimenting with that now. And I'd like to get to a point where, given almost any platform, which could be different types of instances in the cloud, could be smartphones, could be tiny ML devices, or what have you, you know, we can do something that's fairly automated. We're given a data set and given a hardware platform, we can develop something that's ideal. And I've mostly talked about neural net design, but there are also other complementary things like sparsification and quantization that I'd like to roll into this as well. So, okay, that's the end of the talk, and I see I have lots of questions. Sujit, do you want to help me pick questions, or should I just go through them?
Yep, absolutely. So, yeah, thank you, Forrest, for really such an engaging talk and walking all of us through the journey of adopting vision modules as well, right? So convolutional models. And I think this space is a lot larger than maybe swapping out fully connected layers with convolutions, right? So there's a whole domain of computer vision research that we can quickly adopt and just try out different things as you've indicated in your future work. So yeah, thanks again for the engaging talk. Yeah, in the Q&A, I'm mostly filtering based on the likes we've received, and I think let's start with Stephen Yun's question because that was the last remark you made. So what he asks is, what about the other techniques such as quantized network? You touched on that. Network pruning, like the hypothesis ticket paper, distillation. Does pruning give worse models than network architecture search and so on? So maybe you can go into a bit more details on this.
Good. I'm just trying to pull up the question myself so I can make sure I don't forget anything about it. Oh yeah, I see it. Okay, great. Yeah, there's a lot to unpack here. It sounds like, you know, you probably have, hopefully you're already doing some of this because it sounds like you've really thought about this, which is great. So let's see where to start. So the first thing he brings up is, you know, quantization. So for training, as well as, sorry, yeah, for training, we actually used 16-bit for pre-training, particular. And on mobile devices, I'm very interested to integrate Q and NPAC or something similar, or sorry, X and NPAC or something similar into the code base I'm working with for mobile, which, you know, just in a CVPR paper this year, X and NPAC was shown to provide superior results in sparse networks. And so sparsification has been something where It's been difficult to get speedups even on mobile, but much less on GPUs. And I think people are getting more creative with that, so that's great. And in terms of integer, there's this paper called QBERT, which came from some good friends of mine at UC Berkeley. And in QBERT, I think they do a few things right. So they're doing, QBERT stands for quantized BERT. And I think so much of the quantization community has focused on the problem of purely how small can I make the network to store it on disk, which has value. I think if you're transmitting an app update or something, that's useful, so forth. But QBERT and there's other work called Hawk, HAWQ, from the same people. They're extremely focused on speed, and so they're getting significant speed ups in their published work, even better in unpublished work that I believe is coming soon, for vision, but also for BERT and transformer networks and NLP. So I'm very interested to integrate that, and I think they are they seem to be on the cusp of really demonstrating the full stack, all the way down to 8-bit or 4-bit implementations that don't do the questionable thing of accumulating in 32-bit or something, which on many hardware platforms slows things down. So anyway, that's a bit of a ramble, but I think, yeah, there are lots of opportunities in quantization and pruning or sparsification that I'm very interested to adopt myself and maybe improve myself. And then you mentioned the lottery ticket hypothesis paper. So yeah, I think my interpretation of lottery ticket hypothesis is you know as you train, you try to sparsify, right? And there are sophisticated things with rolling back a few iterations and different things like that. But basically, it's a sparsification technique that endeavors to get superior accuracy versus model size trade-offs. But I think to fully exploit the improvements in sparsity, whether or not it's based on lottery ticket hypothesis or other approaches, we need to continue to improve implementations of sparse neural networks. Yeah, I'm probably going on too long about this, but I want to make one last comment, which is, Stephen, you also sort of talk about, model network pruning and neural architecture search and model design. They're all different sides of the same problem, where you could imagine you start with an infinitely large network and then figure out, well, get rid of most of it, what should be left. So I found that I've never seen better results than when I first start out with a highly efficient network, which may or may not be designed from architecture search, and then try to prune it and quantize it. I think if you try to take a really large network and just prune it or quantize it without thinking about better network design, you're usually leaving a lot on the table, is my experience. Okay, so do you want to go to the next question?
Yep, awesome. Thank you, Forrest. So here's an interesting question, and this is a question I had as well, is how do you characterize training efficiency versus inference efficiency? The specific question by Guolier is, does the same speed up number 4x faster on evaluation also hold for training? I imagine not, especially if you're training with GPUs using group convolutions, but that this is a question that I have as well.
Yeah, I'm so glad you asked. Yeah, I should have explained this better in the talk. I didn't for some reason, but yeah, that's your intuition is correct. That on GPUs, at least with the current implementations and the current GPU designs, really struggle with speedups on group convolutions in vision, and they also struggle with group convolution speedups in NLP. So I think we might have seen a very small speed up in training going to groups, 5 or 10% or something, but not 4x. If you were training on a mobile device, which actually could be something worth doing, if you look at the interest in self-supervised learning and privacy-preserving neural networks, I think there you would see this kind of speed up. But I think for GPUs, we may need some different approaches if we want to see a big speed up there. But encouragingly, I've been looking into the GraphCore competitors hardware to NVIDIA, and GraphCore themselves are reported, for regular, ResNet or BERT network, they have a similar compute versus energy costs, but for groups, graph core is getting big speed ups and big energy savings where NVIDIA is not. So I think there definitely are novel things emerging that could make even the approach that we've shown today much more efficient in training.
Awesome, thank you. And related to that, I think is another interesting topic, which is, and again, open-ended, is a question by Casey Tung, which is, do you think non-gradient descent optimization techniques have some potential?
I don't know. I mean, it depends how far you want to zoom out, right? So I think in terms of the immediate applications of, let's try to classify some sentences or classify some pictures or generate some media like that. I haven't yet seen anything that's just totally blown fancy versions of gradient descent out of the water. I think a lot of the work that's described as second order methods still is heavily influenced by just traditional gradient descent, with some Hessians computed and things. It's good work and that's helped a bit, but nothing that requires you to kind of start over in your optimizer design. So basically thinking myopically for the next couple of years, or taking the tools we have and trying to rearrange them. If by the way, if you have like good ideas for other optimizers, I'm super interested. But I'm not personally aware of some of that interesting directions there. However, I think on the more grand quest towards how would we create general intelligence, or how do we really get some common sense baked into machine learning models, these kinds of questions. I do think some entirely different thing that may not have training data in traditional sense, or stochastic gradient descent in traditional sense may be necessary. I just don't know what that thing is going to be.
Yep, awesome. Yeah, that sounds great. There's an interesting question by Ilya Zarkov on efforts to replacing soft attention in transformers with hard attention for speed up. And what are your thoughts on that? So
I actually don't know the definition of hard and soft attention. Maybe someone could enlighten me.
I'm assuming I'm not quite familiar either, but my assumption is some notion of binarization of some sorts, or like a gated attention as opposed to like the softmax or something along those lines.
Oh, I see. Yeah, I guess I'm not super familiar with this line of inquiry, but I guess my blanket answer would be, I don't think there's any reason to believe the current attention layers people are using are optimal. I think there probably will be big changes in the next few years based on some breakthroughs. So yeah, I mean, basically, I think computer vision, to the question that was asked before about is neural architecture search hitting a plateau, I think the problem actually is more computer vision isn't advancing as quickly as it was a few years ago. And so therefore, any activity in mainstream computer vision tasks, including doing architecture search, then doesn't generate as big of improvements as they used to. But I think in NLP, it feels so much like computer vision 5 or even 8 or 9 years ago, when the approaches were so fresh that it was like you could try anything and there was some decent chance that you'd stumble on some breakthrough or some improvement. And NLP feels the same way. It's like, generate a list of 10 ideas of what to try, and try all of them. And I bet 2 or 3 of them actually will produce surprising, results, maybe better accuracy or maybe some other dimension of breakthrough. So yeah, definitely play around with attention. It's probably there are better things that we could do than the current approach.
Cool. Thank you for that, Forrest. There is one question specific to the talk, so I do wanted to address that, which is on SqueezeBERT, I believe the question is why leave FFN1 with G equals 1? So why is the I think if you just go back to your slides. Yeah, what's the reason for the feed forward, the first layer?
Glad you asked. So these feed forward network layers, if you look very carefully, you'll see that the input and output to if the first feed forward network layer, the number of channels is C, which in the case of BERT-base or SqueezeBERT is 768. The second feed forward network layer has 768 input channels, but 4 times the number of output channels, so like 3072 output channels. And so FFN2 costs 4 times as much to compute in terms of flops as FFN1. And then finally, FFN3 has to ingest, 3072 4 times C channel inputs, and then outputs just the regular 768. So basically, FFN2 and 3 before SqueezeBERT came along each cost 4 times as much as FFN1. So we're kind of balancing it out where we say, okay, now in these terms of flops, these 3 FFN layers all cost the same. And then also, why have groups equals 1 anywhere in the network? We want to ensure that the network has adequate ability to communicate across all the channels, because otherwise you can have something that starts to act more like 4 independent networks. And then an alternative to having groups equals 1, we could stick with groups equals 4. But we could do like a shuffle operation, like was proposed in ShuffleNet, to reorder the channels so that the channels mix nicely. So that would be an alternative.
Awesome. So let's end this with another open-ended question, which is basically how much of the work on efficiency is motivated by climate change and the increasing amount of energy that's necessary to use to power advanced and complex models. And just another note is that Forrest has agreed to stay a bit longer as well. So we can continue with the questions, keep them coming for another 10 minutes or so. But those who do have a hard stop at 3, I just thought we should end with this question.
Excellent. So how important is climate change in all this? I think very important. The numbers I have seen indicate that between 2 and 3% of greenhouse gas emissions in the United States already are from data centers, and that's growing. And that's just data centers. Of course, there are lots of other costs to putting up lots of hardware, including the energy and the water required to make computer chips, and you can look at very large environmental impacts. And so I absolutely think that every aspect of deep learning is something where, especially when the computational costs start to get out of hand, as we've seen. I thought the original BERT was already pretty expensive, but GPT-3 is just really, really expensive. We have to figure out, if we want these capabilities at our disposal, we both from a cost perspective and from an environmental responsibility perspective, we can't continue to do it by boiling the ocean in terms of our compute resources. So that's a big deal to me.
Yep. Yeah, that makes a lot of sense to me. And another question that came up with respect to again more of the nuances, right? Is are you familiar with Song Han's work on hardware-aware transformers, and if so, how does this compare to SqueezeBERT? Great
question. So yeah, Song Han is a good friend of mine. He was actually one of the co-authors of the original SqueezeNet paper, so we've known each other for a long time. So in the SqueezeBERT paper, we do touch on Song Han's work. I believe it's called Light Transformer, I want to say. Anyway, so that work, if I remember correctly, the differences between that and SqueezeBERT are, first of all, it's doing language generation rather than language understanding. At least the paper I'm thinking of, I think it was published in ICLR last year. And so it's more focused, I think, on machine translation or language modeling, which basically means automatically generating the next token or the next sequence, or some combination of those. So different application. And then the other thing is they, if I remember correctly, they used convolutions, but they basically said we're gonna have attention layers, and we're going to have convolution layers, and those will just be separate things in different parts of the network. And in our case, the attention networks now are actually convolutions, so it's a bit different. But yeah, I was certainly inspired by that work to work on this.
Awesome. And along the same lines, here's a question from Renmoy, which is, for memory or computations, do we penalize individual modules separately? So if yes, how is that channelized to individual modules using gradient descent?
Sorry, I didn't entirely follow.
I think the question is, how do you, my understanding of it is, how do you incorporate the cost? It's basically, what's the cost function, and how do you incorporate certain costs into the loss function based on what the module is my interpretation of the question.
Oh, great question. Yeah. I should do a tutorial on that sometime. I think I have not seen a good step-by-step, here's how you do super network-based search starting from scratch. So that's a really good question. Hopefully I can at least answer it a bit for this audience. So or you know, for off the cuff, explain a little bit. So basically, you know, you can imagine each layer during backpropagation, you know, you have cost, right? And so in PyTorch, you propagate, you know, each set of gradients from each layer to the previous one and so forth, but you also sum up the costs across all the layers. And so basically when you're, and the cost, I think, is basically the sum of all the gradients in the layer. And that indicates to the auto differentiation method that these costs all should be taken into account backprop. So this is basically, you know, you write this sum of the costs, and then that tells the auto diff what you want to do. So what we do is, when summing up the costs for each layer where we're doing multiple choices, we also add in the cost of the flops or the memory, or in our case, the latency. And then we also multiply the cost of each layer by a hyperparameter, which we just call the cost multiplier. So you know, what you really want is, you know, if your typical loss is, you know, 0.1, you might want that cost to be a couple orders of magnitude less, like 0.001 or something like that. So you want to kind of choose a cost so that even towards the end of training, when the loss is quite small, that the additional cost that you've added is not dominating the gradient. Because if it does, then it can kind of drown out the actual training that's required. Does that make sense? I guess we won't hear back, but.
Yep, it does to me. So yeah. Thank you for the explanation. Let's wrap up with another open-ended question, and then Forrest, feel free to look through the questions as well if there's anything that I missed, or if there's something that you think requires priority. But one of the questions that I saw is, what models are suitable for privacy-preserving applications? And it's an open-ended question, and I'm curious to hear your thoughts as well.
Yeah, I don't want to pretend to know more than I do about this, but my intuition is that the overall system architecture of privacy-preserving business applications and consumer applications is still being figured out. And in terms of privacy-preserving, it can be, you know, the most extreme case would be that no form of data whatsoever comes back from the user device to the company that created the application, right? And in that case, you really need, I think, your only option really is on-device training. So that limits the scope to things where you can either convince the user to label stuff, or, you know, based on the user's future actions, you can find out very quickly which of the potential things that the model could have output is actually the correct one. So you look at autocomplete. On-device training for an autocomplete system is actually quite feasible, because you know, the user eventually types what they mean in most cases, and then you can say that was the correct answer. So for those sorts of things, you basically want all the same things that you would aim for in an efficient model that can be done, you know, efficiently for inference on the device. It's got to be very, very computationally efficient. It's the same deal there. And then there's also things like federated learning, which at least one instance of that is where the engineers who develop the applications, at the company who's making the app, get some data back from the user, but it's abstracted in some way. So for instance, you might get gradients back from the user to train on, but not the raw data. And again, that has the issue of, well, the user will have had to provide the labels in some fashion then, which narrows the applicability a bit. And then yeah, I think there are a lot of other things beyond that can be done with training in the wild, but yeah, hopefully that's a start.
Yep, that sounds great. So again, thank you.
By the way, I had one more I wanted to answer.
Go ahead,
so,
Forrest.
Ilya Zarkov got back to us about more about his meaning of replacing soft attention with hard attention. I think for intentionally or unintentionally, it appears to be a private message. So I don't know if you've seen this, but he said what he meant was, what would it be like to replace the softmax in attention with an actual argmax? And I think basically, argmax can have some difficult properties with regard to it being differentiable. But if you can resolve that, then argmax probably would work pretty well.
Yep, and I guess there are things like smooth max and so on, right, where you can, which is not too different from a soft max. So it's interesting how you can try to have a differential component. I also believe he might mean it on the inference side of things. So again, Ilya, if you, I don't know if you have the time to clarify, but basically at inference, can we just swap it out with just an argmax? I believe might be the question as well. So you can train with the differential equivalent, but then maybe at inference you swap it out with just the argmax.
It could work. If you try it, I'm super interested to hear what the results are.
Yep. Awesome. Well, thank you, Forrest. Thank you for your time. Thank you for such an elaborate talk and an engaging talk, really. And the future work especially opens up an entire research domain, in my opinion, where we can borrow techniques, not just from computer vision into NLP, right? But there are also recent trends where techniques from natural language processing, such as attention mechanisms and sort of the transformer architecture, being borrowed into computer vision. So hopefully there's some sweet spot where we bring in efficiency and hardware and maybe the economics of it all at the end of the day. Normally we'd applaud in a lecture room, but thanks again. This is a virtual applause for such a elegant talk, in my opinion. I'd also like to thank Stephen and Henry, who are production specialists, and really this team's live event wouldn't have been possible without their support and commitment, right? And COVID, these are interesting times with COVID-19, and Teams Live and Microsoft as a whole has made these kinds of talks happen. I saw that there are hundreds of people who attended this talk, and so in some sense, the talks continue and they're accessible, maybe more than ever. So thanks again, Forrest, Stephen, and Henry.
Thank you, and thanks for your attention.